If you leave a liquid oil, like olive oil or canola oil or sunflower oil, out exposed to oxygen, it will go rancid. It will become toxic to eat. The longer you leave it out, the more toxic it will become. And that has to do with the fact that oxygen in the air is a very reactive radical that sticks onto those oil molecules. Now, an oil molecule has two parts. One part you wouldn't really recognize just yet. This part on the left with all the oxygens, that will make more sense in organic chemistry too. Ultimately, this is deriving from a molecule called glycerol, and so you can see these will be named glycerides, derivatives of glycerol. What should make sense, what the chemistry that you should be familiar with, are these long hydrocarbon chains. And you have 3 of these attached to that oxygen part. And so it's called a triglyceride. 3 things attached to something that used to be glycerol, so triglyceride. So those oil molecules really would look something like this. Those oil molecules in the olive oil that you left out, here these red spheres are the oxygen atoms, so you can see you have that oxygen area, and then the 3 hydrocarbon tails. The black spheres are carbons and the white ones are hydrogens. And so if you had this at something like room temperature, this would be what that molecule would look a little bit more like. It would wiggle around. Remember that these bonds vibrate 10 trillion times per second, and so this gives you more of a dynamic image of what a triglyceride would look like in your body. So those triglycerides can react with the oxygen in the air. After all, we discussed in a previous video, the video on fire, we discussed how oxygen is a radical. It's actually a diradical. Each of the oxygen atoms in molecular oxygen, O2, each of the oxygens are radicals. Both of them have an unpaired electron on them. And so when you expose something like this triglyceride, this oil molecule, to molecular oxygen, to these radicals, well, then you can do a radical reaction. But where would a radical form on this molecule? We saw earlier in this chapter that the most stable radical is an allylic radical. The least stable radical would be a primary radical, more stable would be a secondary, more stable is a tertiary, but the most stable of all would be an allylic radical. And so when you see this triglyceride molecule, you see these double bonds in those long hydrocarbon chains, and you think, oh no, if I expose this to a radical, it can do a reaction at the allylic positions, the positions that are one atom away from an atom in the double bond, because that's where the most stable radicals would form. That's a very stable radical, so that's a very tempting place for molecular oxygen to attach. Now, when you draw the mechanism for this, you don't have to copy down the whole triglyceride. Just you copy down the reactive part of it, the double bond with the allylic carbons. So here I'll copy down the double bond in this hydrocarbon tail at the top. Now, when oxygen comes close to this has a hydrogen on it. When oxygen comes close, it rips the hydrogen off. It donates its 1 electron, steals an electron from the hydrogen, and so you're going to form a bond between these two, and the other electron in this bond to the hydrogen goes on to the allylic position to give you that resonance stabilized radical, allylic radical. So the product you'd have at this point would be this bond would break, one of the electrons would go onto this allylic carbon. The other electron would combine with the lone electron on oxygen to form a bond to that. Okay, well, we still have 2 radicals here. We have the oxygen radical and we have this carbon radical. Those can pair up. Those can couple. This one radical donates one electron, the carbon radical donates another. Oh, and before I do this, let me just draw in, just in case you need a refresher. Remember, this radical exists in a p orbital. The pi bond is created by parallel p orbitals. Notice that all three of these p orbitals are parallel. The radical is able to spread out over all three of those atoms, and that stabilizes the charge on the radical. That's why this is a very vulnerable position. That's why oxygen in the air can rip that hydrogen off and form the radical there in the first place. Once you have that radical, the other radical in the oxygen can donate that one electron. That carbon radical can donate one electron. And what you end up with is the two oxygens and a hydrogen bonded to the allylic position. So let's go back to our molecule and actually draw that in. You end up with, two oxygens and a hydrogen bonded to that allylic position. Notice that this is now a peroxide. You have a bond between two oxygens, and that bond is very vulnerable. All it needs to do is be exposed to some heat, for example, your body heat, and that will homolytically cleave and create two radicals in your tissues. So if you eat this triglyceride, let's say you have French bread and you dip it into some old olive oil that you've left sitting out exposed to oxygen, hundreds of trillions of these molecules would wiggle over your tongue, make their way into your stomach. The heat of your body would break that peroxide apart, and now you'd have two radicals that start ripping apart your body tissues, ripping apart the proteins in your cells, your DNA if they get close to it, and giving you a higher likelihood of getting cancer, or in general of just becoming ill. And so that's how oils go rancid. They become peroxides. The oxygen in the air steals a hydrogen from the allylic position on one of these hydrocarbon tails. It creates two radicals. One is the allylic stabilized radical, the radical stabilized through resonance. Those radicals pair up and give you the peroxide. And the peroxide can heat up in your body, break apart to give two radicals in your body. Now, this oxidation step, first of all, this oxidation step requires a double bond. Most triglycerides have at least one double bond somewhere in the hydrocarbon tails. But the difference between saturated fats and unsaturated fats is whether they have that double bond, whether that double bond is common or not. A saturated fat has all single bonds. The single bonds are able to all rotate, and so that these long hydrocarbon tails line up really well, so they pack together really well, and they tend to be solids at room temperature. Saturated fats, with their tails as all single bonds, are things like butter or the fat in a steak, the grizzle in a steak. They're kind of solid. Those are saturated fats. These unsaturated fats have these double bonds that can't rotate. That prevents them from lining up as well. They don't pack together as well, and so they tend to be liquids at room temperature. They don't stick together as much. They don't pack together as much. They're not as dense. So they tend to be liquids at room temperature. So they're things like olive oil or canola oils. In general, unsaturated fats tend to be better for you from the perspective of heart disease. A fat that tends to be solid at room temperature, like a saturated fat that doesn't have these double bonds, it doesn't just tend to be solid at room temperature outside of your body, it also tends to be solid inside of your body and to harden on the inside of your arteries. And that leads to atherosclerosis. The nutrients in your blood will have a harder time getting through your artery walls if they're coated with that fat and feeding your tissues, and the waste products in your tissues will have a harder time getting through the artery wall or through the artery walls into the blood, where they can be brought to your kidneys to be peed out of your body. And as the fat builds up on the inside of your tissues, depending on where the arteries are that fat is, it can lead to different diseases. For example, on a population level, there's an association between those plaques of fat building up on the inside of your arteries. That condition is called atherosclerosis. There's an association between that and Alzheimer's, because there's a small protein in your cerebrospinal fluid called amyloid beta. All of us have it in our cerebrospinal fluids right now, but it's able to get into your, as it builds up, it's able to get into your arteries and then excreted from your body. But when you eat a lot of saturated fats, solid fats, they create plaques on the inside of your arteries, and then that protein can't get through anymore, so it builds up in your cerebrospinal fluid, creates plaques on your neurons, and then those neurons die, and whatever they were responsible for, you lose that function, whether it was memory or perception. So, in general, that was a long detour, but in general, saturated fats tend to be more harmful to your cardiovascular health. And these unsaturated fats, which are liquids at room temperature, are more helpful. They don't create those plaques. They don't tend to create those plaques on the insides of your arteries. And so over time, over a lifetime, they'll allow nutrients to still get through to your tissues, and waste products from your tissues to still get back into your blood more easily. But the thing you have to watch out with these oils, these healthier oils, is that they aren't exposed to oxygen. Because saturated fats, in general, don't undergo this reaction. They don't have a double bond, so they don't have an allylic position, so they won't form a stable radical. But unsaturated fats, the oils, do have these double bonds. And so the longer they're exposed to oxygen, the more peroxides form on them. There's one other thing I want to note about this reaction, and that is that you have this oxygen and triglycerides don't just combine outside of your body. Both of those things also exist inside of your body. Take a deep breath in. Think of the almost unfathomable number of oxygen atoms that are coursing through your nose. To give you an idea, one red blood cell can carry around 1 billion oxygen molecules, 1 billion oxygen radicals. And at any time in your body, you have around 25 trillion red blood cells. In a second, every second, your body makes around 2 million red blood cells, and 2 million red blood cells die. Each red blood cell can carry 1 billion oxygen radicals. Think of the number of radicals that are coursing through your tissues right now. Now, your body has a way to cope with those really reactive molecules, and we'll talk about that in the next 2 videos. Antioxidants. But if you don't get a lot of antioxidants, or if your body is producing a lot of radicals, one of the pieces of evidence, one of the ways that you can diagnose that condition, that oxidative stress in a person's body, is by how many peroxides are in their fats in their body. How many peroxides form in their fats in their body. So you can use this reaction first to be careful about what you eat, but second, as a physician or as a researcher, to measure how much oxidative stress, how much damage radicals are doing inside of a person's body.